Picture the gap between two galaxies. Not the galaxies themselves, not the billions of stars, not the glowing spiral arms you've seen in photographs 1,000 times, but the actual space in between. The stretch of nothing that separates one island of stars from the next, sometimes for millions of light years in every direction. Here's the question I want you to actually sit with before we go any further tonight. What is actually out there in that gap? Not what you assume is out there. What's genuinely physically present if you could somehow travel to the exact midpoint between two galaxies and look around. Drop your honest guess in the comments. Empty vacuum, absolutely nothing at all, or something else. Because the real answer involves a mystery so significant that astronomers spent the better part of 2 decades trying to solve it. And part of the answer wasn't confirmed until surprisingly recently. If you're the kind of person who wants the complete honest picture of what fills the vast majority of the universe's actual volume, go ahead and subscribe, because that's exactly what tonight's video is going to walk through. Think about how much of the universe this question actually covers before we even get into the answer. Galaxies, as spectacular as they are, take up a genuinely tiny fraction of the total volume of space. If you could somehow spread the universe's matter out evenly and asked what the typical patch of space actually looks like, the honest answer wouldn't be a glittering spiral of stars at all. It would be exactly the kind of vast, dark, largely empty gap we're talking about tonight. The kind that separates one galaxy from its nearest neighbors by distances so large that light itself, the fastest thing in the entire universe, takes millions of years just to cross them. Consider the Andromeda Galaxy, our own Milky Way's nearest large galactic neighbor, close enough on cosmic scales that the two galaxies are actually gravitationally bound and slowly approaching each other, destined to eventually merge billions of years from now. Even that relatively close neighbor sits roughly 2.5 million light-years away, meaning the light reaching your eyes tonight, if you spotted Andromeda in a dark sky, left that galaxy 2.5 million years ago, long before modern humans existed at all. Back when our own ancestors were still early, small-brained hominids only beginning to walk upright across the plains of East Africa. And Andromeda counts as close, in cosmic terms, one of the nearer, more crowded corners of our own local neighborhood of galaxies, a small cluster astronomers simply call the local group, containing dozens of galaxies of varying sizes bound together by their mutual gravity across a region of space that, while enormous by any everyday standard, is genuinely modest compared to the scale of the universe as a whole. Reach out further toward galaxies without the benefit of belonging to our same tightly bound local cluster. And the gaps stretch out even further still, sometimes by orders of magnitude, into stretches of space so vast that even light, crossing at its unbeatable universal speed limit, needs tens or hundreds of millions of years just to make the journey from one galaxy to its nearest, genuinely distant neighbor. In a very real sense, understanding what fills that gap isn't a niche question about some obscure corner of astronomy. It's a question about what the overwhelming majority of the universe, by sheer volume, actually consists of. Here's the assumption almost everyone carries into this question without ever examining it closely. We picture the space between galaxies as the purest, most complete kind of nothing the universe has to offer, an absolute vacuum, empty in the most total sense that word can mean. The way you might imagine the inside of a sealed, drained container with every last molecule of air pumped out. It's a reasonable assumption. Honestly, galaxies are the things we photograph, study, and name. The space between them gets treated, almost by default, as the boring leftover part, the blank background a galaxy portrait gets printed on. Nothing more. It's worth noticing where this assumption actually comes from too, because it's not really an assumption anyone consciously reasoned their way into. It's more of an accident of how we happen to encounter astronomy visually in the first place. Every photograph of deep space you've ever seen, whether captured by a professional observatory or a powerful amateur telescope, is specifically composed, framed, and processed to highlight the bright, interesting objects, the galaxies, the nebulae, the star clusters, while the vast surrounding darkness simply reads as an undifferentiated black backdrop. Because there's genuinely very little for a camera to capture there, given how faint and diffuse everything actually filling that space turns out to be. Consider how even the most celebrated deep space photographs are actually constructed. Long exposure times, sometimes stacking hours or even days of accumulated light collection, are needed just to make faint galaxies visible at all, and even with all of that effort, the intergalactic medium itself, spread across such enormous volumes and at such staggeringly low densities, remains completely invisible in ordinary optical photographs, no matter how long the exposure or how sensitive the camera. It's not that photographers are choosing to leave it out of the frame. It genuinely doesn't produce enough visible light of the kind an ordinary camera or even most professional optical telescopes can detect to show up at all, requiring instead the specialized X-ray instruments and careful absorption line techniques we're about to discuss. We've been trained, entirely reasonably, by decades of astronomical imagery to treat that black backdrop as synonymous with true emptiness, when it's actually closer to a photograph of a room that's genuinely quite full, just filled with something too faint for an ordinary camera or an ordinary photograph to properly capture. That assumption isn't entirely wrong, but it's far less complete than it feels, and getting the full picture requires us to actually define what empty means with some real precision. Because it turns out empty comes in dramatically different degrees, and the space between galaxies, while genuinely far emptier than almost anywhere else you could imagine, isn't the same thing as true, absolute nothingness at all. Let's start with something you can actually compare this to, because human engineers have spent the better part of a century trying to create the emptiest possible spaces here on Earth. And understanding just how hard that's been gives you a genuinely useful yardstick for everything we're about to cover. Ordinary air, the stuff filling the room you're sitting in right now, contains something in the neighborhood of 10 to the 20 fifth power molecules in every single cubic meter, a number so large it barely means anything stated plainly, roughly a quintillion times a quintillion. That's what full of air actually looks like at the molecular level. An almost incomprehensibly dense swarm of individual particles constantly colliding, bouncing, and filling every available bit of space. Now, engineers building the most advanced vacuum chambers on Earth, the kind used for testing spacecraft components or conducting sensitive physics experiments, can pump that number down dramatically, removing the overwhelming majority of those molecules, creating what's sometimes called an ultra-high vacuum. Facilities like the ones used to test satellite components before launch, or the beam pipes inside particle accelerators like the Large Hadron Collider, represent some of the most extreme, deliberate emptiness human engineering has ever achieved, requiring specially designed chambers built from materials chosen specifically because they release almost no trapped gas of their own, along with pumps running continuously for hours or days just to remove the last stubborn traces of matter clinging to the chamber's inner surfaces. Even the metal walls of these chambers at a molecular level are constantly, slowly releasing tiny amounts of trapped gas back into the supposedly empty space inside. A process called outgassing, meaning engineers aren't just fighting to remove existing molecules. They are fighting an ongoing battle against the container itself, quietly leaking material back in, one stray molecule at a time, for as long as the chamber remains in use. It's a genuinely humbling engineering challenge once you think it through properly. Every physical container humans have ever built is, at some level, made of the exact kind of ordinary matter that wants to shed a few stray molecules under the right conditions, meaning the very act of trying to build a container empty enough to call a true vacuum runs directly into the stubborn physical reality that containers themselves are never perfectly inert, never perfectly sealed at the molecular level, no matter how carefully designed or expensively constructed. The best vacuum chambers humans have ever built can get down to somewhere around 10 to the 16th power molecules per cubic meter. Still an enormous number in absolute terms, 10 million billion molecules crammed into a single cubic meter of supposedly empty space. But a reduction of roughly 1 billion times compared to ordinary air. That's genuinely impressive engineering, requiring extraordinarily precise sealed chambers, careful material selection, and pumps capable of removing gas molecules faster than they can leak back in from the chamber's own walls. And even that represents the absolute limit of what humanity's best vacuum technology has ever achieved. The emptiest space we know how to deliberately create. Here's the detail that should immediately reframe how you think about tonight's question. The space between galaxies is emptier than that. Not slightly emptier. Dramatically, almost unbelievably emptier, by a margin that makes humanity's best laboratory vacuums look, by comparison, nearly as crowded as a busy city street. In the deepest cosmic voids, the truly vast, largely empty regions of space between the great filaments and clusters of galaxies, the density of matter drops to somewhere around a single particle per cubic meter. One, not 1 billion, not 1 million. One single atom, on average, occupying a cubic meter of space, a volume roughly the size of a washing machine in the emptiest regions of the cosmos. Sit with that comparison for a second, because it's worth letting the scale actually land. Earth's very best vacuum chambers, built with decades of careful engineering specifically to remove as much matter as physically possible, still contain roughly 10 million billion times more matter in the exact same volume than the emptiest regions of space between galaxies. If you shrunk that entire difference down to something you could picture directly, imagine every single grain of sand on every beach on Earth representing the molecules remaining in our best laboratory vacuum. And then imagine representing the emptiest cosmic voids by comparison as a single, solitary grain of sand sitting alone, somewhere on a beach that otherwise doesn't exist at all. That's roughly the scale of difference we're talking about between humanity's best deliberate attempt at nothingness and what nature casually produces across the overwhelming majority of the universe's actual volume. It's worth pausing on how strange that comparison actually is, once you let it sink in properly. Every single achievement of vacuum engineering, every carefully sealed chamber, every specialized pump, every material chosen specifically to outgas as little as possible, represents decades of dedicated human effort pushing against a stubborn universe that keeps insisting on filling any container with at least some trace of matter, no matter how carefully you try to empty it. And after all of that effort, all of that engineering ingenuity, we still fall dramatically short of what nature achieves, apparently effortlessly, across regions of space larger than anything humans could ever hope to physically enclose. There's something almost humbling about that comparison once you actually sit with it. An entire branch of applied physics and engineering, staffed by genuinely brilliant researchers, backed by decades of accumulated institutional knowledge about materials science, sealing technology, and pump design, working specifically toward the singular goal of creating the emptiest possible enclosed space, still can't come close to matching what the universe simply produces, without any effort or intention at all, across the overwhelming majority of its own volume. Nature isn't trying to build the emptiest possible container. It's simply the natural, default outcome of how matter happened to be distributed across the vast majority of the universe's volume, and it still leaves our best deliberate efforts looking almost comically crowded by comparison. So if your first guess to tonight's opening question was something like basically nothing, an almost perfect vacuum, you were considerably closer to correct than most people's intuition would suggest, and genuinely closer to correct than the popular, oversimplified version of this topic usually gets stated. It's worth acknowledging that instinct honestly, because it's not a bad one. Compared to literally anything else you've ever directly experienced, a crowded room, the ocean, even the thin air at a mountain's summit, the space between galaxies genuinely does deserve to be called close to empty. And anyone whose gut reaction leaned in that direction was tracking the actual physics reasonably well. But almost nothing and literally completely nothing are two very different claims, and the difference between them turns out to matter enormously, both for understanding the actual physics of the universe and for solving one of the more genuinely significant mysteries in modern astronomy. A mystery that took decades to even properly formulate, let alone resolve. That gap between almost empty and completely empty is exactly where the missing baryon problem, the warm-hot intergalactic medium, and the entire structure of the cosmic web all end up living. And it's a gap worth taking seriously rather than rounding down to zero out of convenience. Let's actually build out what that almost but not quite nothing consists of, piece by piece. Because the specific ingredients turn out to be genuinely fascinating, connecting all the way back to the earliest moments after the Big Bang itself. The most basic component-filling intergalactic space is simply gas, overwhelmingly hydrogen with a smaller amount of helium mixed in. The same two elements that made up almost the entire composition of the universe in its earliest minutes, before stars had formed and begun the long, patient work of fusing lighter elements into heavier ones. This is genuinely the original leftover material from the universe's birth, largely unchanged in its basic chemical composition for well over 13 billion years, drifting through the vast spaces between galaxies in a form not all that different from what it looked like in the universe's earliest infancy, before the first stars ever ignited and started forging the heavier elements that eventually made up planets, and eventually you. It's worth sitting with the sheer age of that material for a second, because it's easy to let a phrase like 13 billion years old wash past without actually registering the scale of it. Every single hydrogen atom drifting quietly through the space between two distant galaxies right now has existed, essentially unchanged, since roughly the first few minutes after the Big Bang itself. Older than every star, older than every planet, older than every element heavier than lithium anywhere in the observable universe. Compare that to the atoms making up your own body, most of which, aside from the hydrogen, were actually forged much later inside the cores of long-dead stars, cooked slowly over millions of years through nuclear fusion, then scattered across space in a supernova explosion, before eventually gathering together along with countless other scattered atoms into the specific arrangement that eventually became you. The hydrogen drifting between galaxies skipped that entire dramatic stellar journey, remaining instead in almost exactly the same basic state it was left in during the universe's very first moments. A kind of cosmic time capsule that never got recruited into a star, never got cooked into something heavier, and simply continued drifting, largely undisturbed, for the entire subsequent history of the universe. It's simultaneously some of the oldest, most unremarkable material in existence, and also, in its own quiet way, one of the most direct physical links we have back to the universe's actual, literal birth, drifting largely untouched through the emptiest regions of space for the entire subsequent history of everything. This diffuse material, spread across the vast stretches of space between galaxies, is what astronomers call the intergalactic medium, and it's not uniformly distributed. It's genuinely thin and wispy in the truly empty voids, thickening up considerably as you approach the regions where galaxies actually cluster together, following an underlying structure we're going to get into properly in a moment. Even in its thicker regions, though, this gas remains almost unimaginably diffuse by any everyday standard. Typically somewhere in the range of 10 to 100 atoms per cubic meter in the more populated intergalactic regions, still overwhelmingly emptier than anything we can produce in a laboratory, even while representing a meaningfully denser environment than the near-total emptiness of the deepest voids. Here's where the story gets genuinely interesting, though. Because this diffuse intergalactic gas isn't just sitting there quietly at a comfortable, cool temperature the way you might picture leftover cosmic debris behaving. A significant portion of it is scorchingly hot, heated to temperatures between roughly 100,000 and 10 million degrees. Hot enough that individual hydrogen atoms can't hold on to their electrons at all, existing instead as a stripped-down plasma of bare protons and free electrons, zipping around independently rather than bound together into stable atoms. That temperature range deserves a moment of real appreciation, because it's genuinely counterintuitive that some of the emptiest material in the entire universe would also rank among its hottest. 10 million degrees is comparable to temperatures found deep inside stars, hot enough to sustain nuclear fusion under the right pressure conditions, and yet this material isn't glowing brightly the way you'd expect something that hot to behave. Because temperature and brightness depend on more than just how fast individual particles are moving. They also depend on how many particles are actually present to collide, radiate, and produce detectable light. Think about the difference between a single spark and a roaring bonfire. Both can involve individual particles moving at genuinely extreme temperatures, but a single spark, isolated and sparse, simply doesn't produce enough total light for you to notice it from any meaningful distance, while a bonfire, packed with countless particles all radiating simultaneously, lights up an entire campsite. Now imagine trying to spot a single solitary spark, floating in complete isolation from a mile away in complete darkness, with no other sparks anywhere nearby to add their light to it. That's roughly the scale of challenge astronomers faced trying to detect the WIM directly through its own faint glow, before they eventually switched to the far more sensitive absorption technique we're about to discuss, which doesn't require catching the material glowing brightly on its own at all. The warm, hot intergalactic medium is closer to an almost unimaginably vast field of individually scorching sparks, spread across such enormous distances, with so few particles in any given cubic meter, that even though each individual particle really is moving at temperatures comparable to the interior of a star, the total light produced across any observable patch of sky remains extraordinarily faint, detectable only with instruments specifically built and pointed with exactly this challenge in mind. A gas this thin, even at 10 million degrees, simply doesn't have enough particles packed into any given volume to produce the kind of intense, easily visible glow you'd associate with something that hot under ordinary, denser conditions. Which is exactly why this material managed to hide from astronomers for so long, blazing hot and yet almost invisible at the same time. Astronomers call this specific component the warm, hot intergalactic medium, often shortened to the acronym WIM, and understanding exactly why it's there, and exactly how astronomers eventually managed to detect it, takes us straight into one of the more genuinely compelling detective stories in modern cosmology. Here's the mystery that set this entire chapter of astronomy in motion. Starting in the late 1990s and continuing through the 2000s, cosmologists working out the detailed physics of the early universe developed an extremely precise, extremely well-tested prediction for exactly how much ordinary matter, the kind made of protons, neutrons, and electrons, physicists call this category baryonic matter, should exist in the universe overall. This prediction came from multiple independent lines of evidence converging on the same answer. Careful analysis of the cosmic microwave background, the ancient light left over from the universe's infancy, and detailed studies of how the lightest elements, hydrogen, helium, and a trace of lithium, were forged in the universe's first few minutes, a process called Big Bang nucleosynthesis. It's worth appreciating just how remarkable it is that these two completely different approaches agree with each other at all. One method involves analyzing the faint, precise pattern of temperature variations in light that's been traveling across the universe for nearly 14 billion years. The other involves working out, from nuclear physics' first principles, exactly how much hydrogen would have fused into helium and trace amounts of lithium during the universe's first few minutes of existence, when temperatures and densities were high enough for nuclear fusion to occur freely throughout all of space, before everything cooled and spread out too much for the process to continue. These two methods don't share instruments, don't share observational techniques, and were developed by largely separate communities of researchers working through completely different chains of physical reasoning. One traces its predictions back to conditions roughly 380,000 years after the Big Bang, when the universe first became transparent to light. The other traces its predictions back to conditions in just the first few minutes after the Big Bang, an era so early and so extreme that nuclear reactions themselves were still actively reshaping the raw material of the cosmos. Getting two such wildly different methods, probing two such wildly different moments in cosmic history, to land on essentially the same final answer for how much ordinary matter the universe contains is exactly the kind of cross-validation that gives scientists genuine confidence in a result. The equivalent of two witnesses, questioned separately, with no opportunity to compare notes, independently describing the same underlying event. Both approaches, developed independently using completely different physics and completely different observational techniques, converged on remarkably consistent answers for exactly how much ordinary matter the universe should contain. a level of agreement between two totally separate lines of evidence that gave cosmologists enormous confidence the underlying prediction itself was correct. But when astronomers actually went out and tried to add up all the ordinary matter they could directly observe in the relatively nearby present-day universe, stars, galaxies, gas clouds, everything visible or detectable through conventional means, they came up dramatically short. Roughly half of the ordinary matter the universe was supposed to contain. Based on those extremely well-tested early universe predictions, simply couldn't be found anywhere astronomers had looked. This kind of discrepancy is exactly the sort of thing that makes a good scientific mystery genuinely interesting, rather than simply a case of sloppy measurement somewhere along the way. It wasn't a small, easily dismissed rounding error. The kind of minor discrepancy that gets explained away by slightly improving a telescope's calibration or double-checking a calculation. It was a substantial, consistent, roughly 50% shortfall, showing up again and again across multiple independent surveys, using different telescopes, different techniques, and different teams of researchers working largely independently of one another. All converging on the same troubling conclusion: half of the universe's ordinary matter was, as far as anyone could tell, simply not where it was supposed to be. Not missing in some vague, hand-wavy sense, but missing in a precise, quantifiable way. A specific percentage of predicted matter that observational surveys, however carefully and thoroughly conducted, kept failing to actually locate anywhere in the visible universe. This became known with a certain amount of dry astronomical humor as the missing baryon problem, and it genuinely puzzled cosmologists for years. The theory predicting how much ordinary matter should exist was, and remains, one of the most successful, most precisely tested frameworks in all of physics, making it deeply unlikely that the theory itself was simply wrong. That left an unsettling alternative. The matter had to actually be out there somewhere. In some form, astronomers simply hadn't figured out how to properly detect yet. Hiding in plain sight across the vast majority of the universe's volume, the space between galaxies, in a form too faint, too diffuse, or too difficult to observe using the techniques astronomers had relied on up to that point. The specific reason this hot, diffuse gas proved so difficult to detect comes down to a genuinely frustrating combination of physical properties working against astronomers from every angle at once. Gas at 10 million degrees does emit radiation, but overwhelmingly in the form of X-rays, and specifically extremely faint, low-energy X-rays that get absorbed almost immediately by any intervening material, including, unhelpfully, the thin haze of gas and dust sitting inside our own Milky Way galaxy, directly in the line of sight for essentially every observation astronomers might want to make. On top of that, the material is so sparse, remember. We're talking about somewhere in the range of 1 to 10 particles per cubic meter. That even when it does emit detectable radiation, the total amount of light coming from any given patch of it is vanishingly small, spread out over such an enormous volume that concentrating enough signal to actually detect it required instruments and techniques that simply didn't exist yet when the missing baryon problem was first identified. Astronomers eventually found a clever workaround, one that didn't rely on catching this hot gas glowing on its own, but instead used it to cast a very faint shadow. Distant, extraordinarily bright objects called quasars, powered by supermassive black holes actively feeding on surrounding material at the centers of faraway galaxies, produce light bright enough to shine clearly across billions of light years. As that light travels toward Earth, passing directly through any warm, hot intergalactic medium sitting along the way, specific wavelengths of that light get absorbed by oxygen atoms present in small amounts within the WIM, leaving a faint, very specific fingerprint in the quasar spectrum. A telltale dip at exactly the wavelength that particular species of ionized oxygen would be expected to absorb. Think of it a bit like standing far away from a lighthouse and noticing that the beam looks very slightly dimmer and a very specific shade darker. Exactly at the moment thin, high clouds happen to drift directly between you and the light. You're not looking at the clouds directly, and the clouds themselves might be almost invisible against the night sky on their own. But their effect on the lighthouse beam passing through them is real, measurable, and specific enough that a sufficiently careful observer could work out exactly what kind of cloud was there, purely by studying how it altered the light passing through it. Astronomers essentially built an equivalent of that careful cloud-watching observer, except working with light that had traveled billions of years instead of a beam crossing a harbor, and looking for a specific, precise dip in brightness at exactly one narrow band of wavelengths, corresponding to the exact energy oxygen atoms in a particular ionization state are known to absorb. Rather than a general dimming across the whole beam, it's an extraordinarily precise kind of detective work, requiring instruments sensitive enough to measure light brightness across thousands of individual, narrowly defined wavelength bands simultaneously, then carefully checking whether any of those bands showed exactly the specific pattern of absorption a passing cloud of warm, hot intergalactic gas would be expected to leave behind. Rather than trying to see the WIM directly glowing against the black backdrop of space, astronomers learned to look for its faint absorption signature imprinted onto the light of something else shining brightly behind it. The cosmic equivalent of detecting a nearly invisible pane of tinted glass by noticing how it subtly dims and colors the light passing through it, rather than trying to see the glass itself directly. This approach finally paid off with real, statistically solid detections. In 2018, a team led by astrophysicist Fabrizio Nicastro published results in the journal Nature reporting a genuinely convincing detection of WIM material using this exact absorption technique, examining the X-ray spectrum of a distant quasar and finding clear evidence of oxygen absorption at precisely the wavelengths and redshifts expected if warm, hot intergalactic gas was sitting along that line of sight. It's worth appreciating just how much careful, patient work went into a result like this. Researchers had to identify a suitably bright, suitably distant quasar to use as a backlight in the first place, obtain enough telescope time on sensitive enough instruments to actually resolve the extremely faint absorption features involved, and then rule out every plausible alternative explanation for the specific dip they found in the quasar spectrum, before finally being confident enough in the result to publish it as a genuine detection rather than just an intriguing but inconclusive hint. Further work over the following years, including direct X-ray emission measurements of cosmic web filaments published in 2020, and considerably more comprehensive survey work published in 2024 using a dedicated space telescope specifically built to map X-ray emission across large patches of sky, has continued to build out the picture, examining thousands of individual cosmic filaments and confirming that the warm, hot intergalactic medium really is present in roughly the quantities needed to account for the universe's missing ordinary matter, with current estimates suggesting the WIM holds somewhere around 40 to 50% of all the baryonic matter in the present-day universe. An enormous share of the universe's ordinary matter, sitting quietly in the space between galaxies. Essentially invisible until astronomers finally worked out exactly how to look for it properly. Now that we've established what fills this space, at least in terms of ordinary matter, it's worth understanding that this gas isn't scattered randomly through the universe, the way you might scatter dust evenly across an empty room. It follows an enormous, genuinely beautiful underlying structure, one that astronomers have spent decades mapping out through painstaking surveys of galaxy positions across the sky, called the cosmic web. Picture the universe's large-scale structure the way you might picture a sponge, or perhaps more accurately, a colossal three-dimensional network of soap bubbles, with galaxies and gas concentrated along the thin, connected walls and filaments of that network, while the interior of each bubble, the vast, roughly spherical regions enclosed by the surrounding filaments, remains almost completely empty, home to none of the galaxies, and very little of the gas, populating the denser regions nearby. Building this map wasn't a quick or easy undertaking either. Large galaxy surveys, projects involving years of dedicated telescope time, carefully measuring the precise position and distance of hundreds of thousands, eventually millions, of individual galaxies across enormous stretches of sky, were required before this underlying structure became clear. Early results, going back to the 1980s, started to reveal hints of this filament and void pattern, showing galaxies weren't scattered randomly at all, but clustered along connected, thread-like structures with enormous, comparatively empty gaps in between. A discovery that genuinely surprised many astronomers at the time, who had generally expected galaxies to be distributed in a much more uniform, evenly scattered pattern across the universe. One of the earliest, most influential of these surveys involved painstakingly measuring the precise distance to galaxy after galaxy along narrow slices of sky, essentially building up a three-dimensional map, one careful measurement at a time. In an era before the kind of automated, large-scale digital surveys astronomers rely on today existed at all. Researchers working on these early projects have described the genuine surprise of watching the resulting maps take shape, expecting something close to a uniform scattering of dots, and instead finding galaxies arranged into clear, connected sheets and filaments with vast, comparatively empty regions carved out in between. A structure nobody had specifically predicted in advance, emerging instead directly from the patient, careful accumulation of real observational data. Since then, increasingly ambitious survey projects have refined that early picture into the detailed, three-dimensional map of the cosmic web astronomers work with today. One confirmed and refined by literally millions of individual galaxy position measurements, gathered by dedicated survey telescopes, purpose-built for exactly this kind of large-scale, systematic mapping project, running for years at a time, methodically working their way through enormous swaths of the observable sky. These filaments, the actual structural threads of the cosmic web, are almost unimaginably large, some stretching somewhere between roughly 500 and 800 million light-years in length. Structures so vast that a single filament can be many thousands of times wider than our entire Milky Way galaxy, connecting clusters of galaxies together like threads of a spider's web stretched across the largest scales the universe has to offer. Try to actually hold that comparison in your head for a moment, because it's genuinely difficult to do justice to in ordinary language. Our own Milky Way galaxy, home to hundreds of billions of stars, An object so large that light itself takes roughly 100,000 years just to cross from one side to the other would appear as barely more than a single, almost invisible speck if you tried to place it against the full length of even a modest cosmic filament, let alone one of the largest ones astronomers have mapped. Zoom out far enough to actually see a full filament in proper context. And every galaxy, every cluster of galaxies, every structure that feels genuinely enormous when you're studying it up close, shrinks down into little more than a faint scattering of individual dots strung along a single connected thread, one of countless similar threads making up the cosmic web as a whole. These aren't just large structures by galactic standards, they're among the largest coherent structures known to exist anywhere in the entire universe, rivaled in scale only by the cosmic web itself. The complete network these individual filaments are simply threads within. It's along these filaments that the warm, hot intergalactic medium tends to concentrate most heavily, gravitationally drawn in and shock-heated as material falls inward from the surrounding emptier regions. Exactly the environment where astronomers eventually manage to detect its faint absorption signature against the light of distant quasars. And then there are the voids, the genuinely empty interiors of this cosmic sponge structure. Vast regions of space, sometimes hundreds of millions of light-years across, containing dramatically fewer galaxies than the surrounding filaments, and correspondingly emptier of even the diffuse intergalactic gas we've been discussing. The nearest such void to our own location in the universe is called, with refreshing astronomical directness, the local void, a genuinely enormous, largely empty stretch of space sitting adjacent to our own region of the cosmic web. Its existence inferred and mapped through the simple, telling absence of galaxies in that particular direction of the sky. A conspicuous gap in the otherwise busy distribution of galaxies surrounding our own corner of the cosmic web. It's genuinely strange to think about the fact that our own Milky Way, along with the broader cluster of galaxies we belong to, sits essentially on the edge of one of these enormous cosmic voids. Close enough that astronomers have actually measured its gravitational influence, a slight, measurable pull our entire galactic neighborhood experiences. Being tugged gently away from that emptier region and toward the denser, more crowded regions of the cosmic web nearby, evidence that even the void's near-total emptiness still exerts a real physical influence on its surroundings, purely through the absence of the gravitational pull that denser regions would otherwise provide. This kind of measurement, detecting a gravitational effect caused specifically by the absence of matter rather than its presence, is a genuinely elegant piece of astronomical detective work in its own right. Researchers had to carefully measure the precise motions of galaxies across an enormous stretch of sky, then work backward, using the well-understood physics of gravity, to figure out what arrangement of mass, including regions with notably less mass than their surroundings, could actually produce the specific pattern of motion they observed. Finding a void this way, indirectly, through its gravitational fingerprint rather than any direct detection of the void itself, underscores just how much of modern cosmology depends on this same basic strategy. Inferring the presence, or in this case, the striking absence, of matter through its effects on everything nearby, rather than ever managing to observe it directly. These voids represent the closest thing the universe actually offers to true, near total emptiness, regions where even the WIMP's already sparse 1 to 10 particles per cubic meter thins out further still, down toward that single solitary particle per cubic meter we discussed earlier, the genuine physical frontier of nothingness within our observable universe. So we've now built out a genuinely solid picture of the ordinary matter filling the space between galaxies, thin, largely leftover hydrogen and helium gas, heated in many places into a scorching, diffuse plasma, arranged along an enormous cosmic web of filaments stretching hundreds of millions of light-years, with genuinely near-empty voids occupying the vast interior spaces of that web structure. That alone would be a satisfying, complete answer to tonight's opening question, if ordinary matter were the whole story. But here's the detail that changes everything we've covered so far. The detail that turns this cosmic web from a loose, gravity-drawn arrangement of gas and galaxies into something with a far stranger, far more fundamental architecture holding the entire structure together in the first place. Every single filament, every void, every strand of the cosmic web we just described exists in exactly the shape and pattern it does because of something else entirely. Something that doesn't emit light, doesn't absorb X-rays, and can't be detected through any of the techniques that finally revealed the whim. Think back to the sponge analogy we used a moment ago. The filaments as connected walls, the voids as the hollow interior spaces. Ask yourself an honest question. Why does the universe's matter arrange itself into that specific pattern at all, rather than spreading out perfectly evenly or clumping into some completely different shape entirely? It's a genuinely good question to sit with for a second before moving on, because the answer isn't obvious just from looking at the pattern itself. A random, undirected process could, in principle, produce all sorts of different large-scale arrangements. Matter clumping into isolated blobs scattered evenly across space, or spreading into thin, uniform layers, or forming any number of other geometric patterns entirely. The specific, consistent filament and void, sponge-like structure the universe actually shows required something with a very particular kind of gravitational fingerprint, guiding matter into exactly this shape over and over again at every scale astronomers have ever managed to survey. From relatively nearby galaxy clusters all the way out to the most distant large-scale structures our best telescopes can currently map. A consistency of pattern that itself is a genuine clue about what's actually responsible for shaping it in the first place. A clue worth following carefully rather than glossing over as simply an interesting curiosity of how matter happens to be arranged. Gravity alone, acting on ordinary matter, the hydrogen and helium gas we've spent this entire conversation discussing, isn't nearly enough to explain it. There simply isn't enough ordinary matter, arranged in a way gravity could act on quickly enough to produce filaments and voids this large, this well-defined, in the amount of time the universe has actually had available since the Big Bang. Something else had to be doing the heavy lifting, quite literally providing the gravitational scaffolding that ordinary matter eventually settled onto, tracing out a shape that was, in a very real sense, already there long before the gas and galaxies arrived to fill it in. Understanding what actually holds this entire cosmic architecture together, and what that means for what's genuinely, physically present in the space between galaxies, is where we're headed next. And it involves a substance so strange, so fundamentally different from anything we've discussed so far tonight, that it makes the warm-hot intergalactic medium's decades-long detection story look almost straightforward by comparison. If ordinary hydrogen and helium gas took 20 years of careful, patient detective work to properly confirm, the substance actually responsible for shaping the cosmic web has resisted direct detection for far longer still, identified so far only through its gravitational effects, never once directly observed, captured, or measured through any conventional instrument. And understanding exactly why that is, and what it means for tonight's opening question, is exactly where this story picks back up, taking everything we've established about diffuse gas, hot filaments, and empty voids, and revealing that all of it, together, still only accounts for a small fraction of what's actually physically present in the vast stretches of space separating one galaxy from the next. The substance responsible for shaping the cosmic web is called dark matter, and I want to be genuinely careful and precise about how we introduce it, because this particular topic gets oversimplified and sometimes outright mischaracterized, more often than almost any other in popular science. Dark matter isn't a wild, speculative guess dreamed up to patch over an inconvenient gap in our understanding. It's the name astronomers gave to a specific, consistent, repeatedly confirmed gravitational effect. Observed across dozens of independent lines of evidence, gathered using completely different techniques by completely different research teams, across nearly a century of increasingly careful observation. The story properly begins in the 1970s with an astronomer named Vera Rubin, who was carefully studying the rotation of spiral galaxies, measuring exactly how fast stars orbited around their galaxy's center at different distances from that center. Rubin worked alongside her collaborator, Kent Ford. Using an especially sensitive instrument Ford had built specifically to measure the faint light spectra of individual regions within distant galaxies, allowing far more precise velocity measurements than had previously been possible. It's worth noting that Rubin herself faced considerable professional obstacles throughout her early career simply because she was a woman working in a field that, at the time, was overwhelmingly dominated by men, having been denied admission to certain graduate programs and observatories purely on the basis of her gender. Obstacles she pushed through anyway, going on to make one of the most consequential observational discoveries in the entire history of modern cosmology. Based on the visible matter in these galaxies, the stars, the gas, everything astronomers could actually see and account for, physics made a clear prediction. Stars far out at the edges of a galaxy's spiral disk should orbit noticeably slower than stars closer to the crowded, mass-dense center. The same basic principle that makes outer planets in our own solar system orbit the Sun more slowly than inner ones, since the gravitational pull holding an orbiting object in place weakens the further out you get from the bulk of the mass doing the pulling. Rubin's careful measurements showed something completely different. Stars at the outer edges of these galaxies were orbiting just as fast as stars much closer to the center. Essentially, flat rotation curves rather than the steadily declining ones Newtonian physics predicted based on visible matter alone, a result flatly inconsistent with the amount of visible matter astronomers could actually account for. Something invisible, something contributing real, substantial gravitational pull without producing any detectable light, had to be present throughout these galaxies, extending well beyond the visible, glowing disk of stars, holding those fast-orbiting outer stars in place through gravity alone. Rubin herself, by most accounts, was initially cautious about the implications of her own results. But as she and other astronomers confirmed the same basic pattern across galaxy after galaxy, dozens and eventually hundreds of them, all showing the same fundamentally unexpected rotation behavior, the conclusion became increasingly difficult to avoid. Rubin's rotation curve measurements weren't an isolated anomaly either. Over the following decades, completely independent lines of evidence kept pointing toward the exact same conclusion, using methods that had nothing to do with measuring how fast stars orbit. Gravitational lensing. The bending of light from distant background galaxies as it passes through the gravitational field of matter sitting in the foreground, an effect Einstein's general relativity directly predicts, revealed that galaxy clusters were bending far more light than their visible matter alone could account for, requiring substantially more mass, invisible mass, to produce the specific degree of bending astronomers actually measured. Gravitational lensing works on a principle that's genuinely elegant once you picture it properly. Massive objects warp the fabric of space around them, and light traveling through that warped space follows a curved path. The same basic effect responsible for the famous 1919 eclipse observation that first confirmed general relativity, just applied on a vastly larger scale here, using an entire galaxy cluster's worth of mass instead of a single star. When astronomers photograph a massive foreground galaxy cluster, they often see distorted, smeared, sometimes multiply-imaged arcs of light, the warped, magnified images of background galaxies sitting directly behind that cluster. Their light bent and distorted on its way to our telescopes. Some of the most striking astronomical images ever captured show exactly this effect. Entire clusters surrounded by faint, curving arcs of light, each individual arc a warped, stretched-out image of some far more distant galaxy, its light bent around the cluster's gravitational field on its way toward Earth, sometimes producing multiple separate images of the exact same background galaxy, each one following a slightly different bent path around the intervening mass. By carefully measuring exactly how much distortion appears in these images, astronomers can calculate, with real mathematical precision, exactly how much total mass the foreground cluster must contain to produce that specific degree of bending. A mass that, again and again, across cluster after cluster, comes out dramatically larger than what the cluster's visible stars and gas can actually account for. And in 2006, one of the most visually compelling pieces of evidence yet emerged from something called the Bullet Cluster, the aftermath of an ancient collision between two massive galaxy clusters. This particular collision turned out to be almost perfectly suited for testing the dark matter hypothesis directly, because it separated two different components of each cluster's mass in a way astronomers could actually observe and measure independently. Astronomers studying this collision found that the visible ordinary matter, the hot gas that makes up most of a cluster's ordinary mass, had been slowed and separated from the bulk of each cluster's total gravitational mass during the collision, based on gravitational lensing measurements, while the invisible mass, whatever it actually was, had passed straight through the collision largely undisturbed. Exactly the behavior you'd expect from a form of matter that doesn't meaningfully interact with itself or with ordinary matter the way colliding gas clouds do, only ever making its presence known through gravity. Picture two clusters of galaxies crashing directly through each other at enormous speed, each one containing hundreds or thousands of individual galaxies, along with vast reservoirs of hot X-ray emitting gas making up most of each cluster's ordinary visible mass. The visible ordinary gas within each cluster being made of particles that do interact with each other through ordinary electromagnetic forces, collided, slowed down, and piled up in the middle of the collision, exactly the way you'd expect two clouds of gas smashing into each other to behave, creating a distinctive bullet-shaped shockwave of superheated gas clearly visible in X-ray images of the collision, which is actually where the bullet cluster gets its evocative name. But when astronomers mapped out where the bulk of each cluster's actual gravitational mass ended up using gravitational lensing, they found it had sailed straight through the collision, essentially unaffected, ending up well ahead of the slowed collided gas on either side. Overlaying the X-ray image of the slowed collided gas directly on top of the gravitational lensing map of where the actual mass turned out to be produces one of the most visually striking, most directly convincing pieces of evidence in all of modern astrophysics. Two distinctly separate, clearly displaced concentrations. The ordinary gas piled up in the collision center, and the true gravitational mass, presumably dominated by dark matter, sitting well to either side, having passed straight through the entire event without slowing down at all. It's one of the cleanest, most visually dramatic pieces of evidence available for dark matter's existence, because it directly shows two different kinds of matter behaving in two completely different ways during the exact same physical event. Exactly what you'd expect if one component genuinely doesn't interact through anything except gravity. Here's how this connects directly back to the cosmic web we spent the first half of tonight's story building up. When cosmologists build detailed computer simulations of how the universe's large-scale structure actually formed, starting from the extremely uniform, nearly featureless distribution of matter present shortly after the Big Bang, and running the simulation forward billions of years using the known laws of gravity, ordinary matter alone simply doesn't produce the filament and void structure we actually observe. There isn't enough of it, and it doesn't clump together fast enough on its own to build structures this large in the time the universe has actually had available. These simulations represent genuinely enormous computational undertakings, some of the largest scientific computing projects ever attempted, tracking the gravitational interactions of billions of individual simulated particles across a virtual volume representing enormous stretches of the actual universe, run on some of the most powerful supercomputers in the world, sometimes taking weeks or months of continuous computation to complete a single simulated run, consuming enough electricity and computing time that researchers have to carefully schedule and justify access to the specific supercomputing facilities capable of running them at all. Some of the more ambitious of these projects have tracked the gravitational evolution of tens of billions of individual simulated particles simultaneously, each one representing a clump of matter far too small to model individually otherwise, requiring careful, sophisticated programming just to keep track of how every single particle gravitationally influences every other particle nearby, across a simulated span of time stretching from the universe's earliest moments all the way up to the present day. A computational challenge so demanding that even modest improvements in the efficiency of the underlying code can save researchers weeks of otherwise wasted supercomputer time. Researchers start these simulations from initial conditions carefully calibrated to match the actual measured properties of the early universe, taken directly from observations of the cosmic microwave background. Then let the laws of gravity, programmed carefully into the simulation, play out over a virtual span of billions of years, watching to see what large-scale structure naturally emerges. The remarkable thing, and the reason these simulations matter so much for confirming dark matter's role in shaping the cosmic web, is that researchers don't get to simply program in the answer they're hoping to find. They start with basic physical laws and basic initial conditions, run the simulation forward, and then compare whatever structure emerges against the real observed universe. A genuine test rather than a foregone conclusion. one where the simulation could, in principle, have failed to match reality at all, had the underlying assumption about dark matter's quantity and behavior been wrong. But add dark matter into those same simulations, in the specific proportions astronomers have independently measured through rotation curves, lensing, and the bullet cluster. And the simulated universe suddenly starts producing exactly the kind of cosmic web astronomers actually observe when they map the real distribution of galaxies across the sky, filaments, voids, and clusters, forming in remarkably close agreement with the real universe's actual large-scale structure. It's a genuinely powerful piece of cross-validation, one line of evidence. The specific quantity of dark matter needed to explain galaxy rotation curves and gravitational lensing, independently predicting an entirely separate observed phenomenon, the specific large-scale shape of the cosmic web itself. A level of agreement that would be an almost impossible coincidence if dark matter weren't genuinely present in roughly the quantities cosmologists currently estimate. Dark matter, in other words, isn't just an interesting side mystery sitting alongside the story of the intergalactic medium. It's the actual scaffolding the entire cosmic web is built on. Ordinary matter, the hydrogen and helium gas that eventually formed the WIM, and eventually galaxies themselves, fell inward under gravity's pull toward regions where dark matter had already begun clumping together, following gravitational contours that dark matter, moving essentially undisturbed by anything except gravity, had already sketched out across the universe long before ordinary matter caught up and settled into the same basic shape. The visible galaxies and glowing filaments of gas we can actually observe are, in a very real sense, simply the parts of an already existing, much larger, invisible structure that happened to become bright enough to see. So what does this mean for tonight's actual question about what fills the space between galaxies? It means that even in the emptiest-looking stretches of intergalactic space, dark matter is present, quietly, invisibly, in genuinely substantial quantities based on current best estimates from cosmology, making up roughly 27% of the entire universe's total mass and energy content, compared to only around 5% for all of the ordinary matter we've spent this entire video discussing. The hydrogen, the helium, the WIM, the galaxies, the stars, everything made of the familiar protons, neutrons, and electrons that build up literally everything you've ever directly touched or seen. These specific percentages come from some of the most precisely measured numbers in all of modern cosmology, derived primarily from an extraordinarily detailed analysis of the cosmic microwave background, carried out by space missions specifically designed to map that ancient light across the entire sky with exquisite precision. These missions spent years continuously scanning the sky, building up an increasingly detailed, increasingly precise map of temperature variations in that ancient radiation. Variations so subtle they amount to differences of only a few hundred thousandths of a degree from one point in the sky to another, requiring instruments cooled to temperatures just barely above absolute zero, shielded carefully from any stray heat that might otherwise wash out the incredibly faint signal being measured. The tiny, subtle patterns and fluctuations in that ancient radiation encode an enormous amount of information about exactly what the universe is made of, information cosmologists have learned to extract with a level of precision that would have seemed almost unbelievable to researchers working just a few decades earlier. Pinning down these composition percentages to within a fraction of a percentage point of uncertainty. The specific pattern of those tiny temperature variations depends, in mathematically precise ways worked out through decades of theoretical cosmology, on exactly how much ordinary matter, and dark energy the universe contains, meaning that a sufficiently detailed map of the cosmic microwave background essentially functions as an extraordinarily precise inventory of the universe's entire composition, read directly off a single ancient snapshot of light. Dark matter outweighs ordinary matter by more than 5 to 1 across the universe as a whole, meaning that if you could somehow tally up everything actually present in the space between two galaxies, dark matter, not the diffuse gas we spent so much time discussing, would represent the single largest contribution to the total mass genuinely sitting out there. It's a genuinely strange thing to sit with. The emptiest seeming regions of the entire universe are, by actual mass, dominated by something we've never directly detected, never captured in a laboratory, and still don't fully understand at the most fundamental particle physics level, even while its gravitational fingerprints are scattered across essentially every scale of cosmic structure astronomers have ever managed to study. Physicists have spent decades trying to figure out exactly what dark matter actually is. At the level of fundamental particles, running dedicated underground experiments shielded deep beneath mountains and inside old mine shafts specifically to block out the constant background noise of ordinary cosmic rays, hoping to catch a single direct interaction between a dark matter particle and an ordinary detector. Some of these detectors sit more than a mile underground in retired mining operations specifically chosen because the sheer thickness of overlying rock blocks out the overwhelming majority of ordinary background radiation, leaving researchers with a rare, quiet enough environment to have any realistic chance of spotting an extraordinarily faint, extraordinarily rare interaction between an ordinary atomic nucleus and a passing dark matter particle, if such an interaction happens at all within the lifetime of the experiment. So far, despite genuinely enormous investments of time, money, and careful engineering, none of these experiments have produced a confirmed direct detection. This isn't a failure of the underlying science, though it can sometimes feel that way from the outside. It's a genuine reflection of just how weakly dark matter appears to interact with anything except gravity. Meaning that even though it vastly outweighs ordinary matter across the universe as a whole, individual dark matter particles pass through ordinary detectors, and through you constantly without leaving so much as a trace, making the search for direct proof one of the most patient, most technically demanding ongoing projects in all of modern physics. It's a strange thought to actually sit with right now as you're reading or hearing this sentence, dark matter particles, if the current best model is correct, are passing directly through your own body, through the chair or bed you're sitting on, through the entire planet beneath your feet, constantly, silently, leaving no trace of their passage at all. Exactly the same undetectable behavior that's kept this substance hidden from every direct search attempted so far, even while its gravitational influence quietly shapes the large-scale structure of the entire observable universe. There's still a substantial portion of the universe's total content we haven't even touched on yet, though, and it's arguably the strangest ingredient of all. Roughly 68% of the universe, according to the same best current measurements, isn't matter of any kind at all, dark or otherwise. It's something else entirely, called dark energy, and unlike dark matter, which clumps together gravitationally into the filaments and structures we've spent tonight discussing, dark energy appears to be spread perfectly, uniformly, evenly throughout every single point in space, with no clumping, no filaments, no voids of its own, simply present everywhere all the time, in exactly the same concentration. This uniform distribution is genuinely one of the strangest properties dark energy has, especially once you compare it directly to everything else we've covered tonight. Ordinary matter clumps into stars, galaxies, and filaments. Dark matter clumps too, just on a larger scale, forming the invisible scaffold underlying the cosmic web. Dark energy does neither. It doesn't care whether it's sitting inside a dense galaxy cluster or in the emptiest depths of a cosmic void hundreds of millions of light years across. Its concentration remains precisely the same everywhere, a property that turns out to be central to understanding why it behaves so differently from every other ingredient in the universe. Gravity's pull growing weaker as matter spreads out and thins with the universe's expansion, while dark energy's overall effect actually grows stronger over cosmic time. Precisely because there's simply more space and therefore more total dark energy as the universe continues expanding. Think about what that actually implies for the very long-term future of the universe, because it's a genuinely strange consequence once you follow the logic all the way through. Early in the universe's history, matter was densely packed together, and gravity's pull, concentrated and strong, dominated over dark energy's comparatively gentle, spread-out push. As the universe expanded and matter spread out and thinned over billions of years, gravity's grip weakened, while dark energy, always present in the same uniform concentration per unit of space, simply had more total space to act across, its overall influence growing steadily relative to gravity's, until sometime around 5 billion years ago. Dark energy's push finally overtook gravity's pull on the largest cosmic scales, and the universe's expansion began accelerating rather than gradually slowing down. Exactly the surprising behavior those 1998 supernova observations managed to catch in the act. Dark energy's existence was confirmed through a genuinely surprising discovery made in 1998 when two independent teams of astronomers, studying distant exploding stars called Type 1a supernovae, a specific kind of stellar explosion reliable and consistent enough to serve as a precise cosmic distance marker, found something nobody had expected. Type 1a supernovae occur when a particular kind of collapsed star called a white dwarf pulls in just enough additional material from a companion star to trigger a runaway thermonuclear explosion, always detonating at essentially the same mass and therefore always releasing an almost identical, predictable amount of total energy, which means astronomers can use their observed brightness compared to their known intrinsic brightness to calculate exactly how far away they are, a genuinely elegant natural yardstick scattered conveniently throughout the observable universe. Astronomers sometimes describe these particular supernovae as standard candles, precisely because of this remarkably consistent intrinsic brightness. The same basic principle behind why you can estimate how far away a lit candle actually is simply by noticing how dim it appears from a distance, provided you already know exactly how bright that specific candle burns up close. A 100-watt light bulb looks dimmer the farther away it sits, in a precisely calculable, predictable way, and if you already know it's a 100-watt bulb, its apparent dimness alone tells you exactly how far away it must be. Type 1a supernovae function as the cosmic equivalent of that known standardized light bulb, scattered by the thousands across galaxies at every distance astronomers have ever managed to survey. Each one providing an independent, reliable distance measurement the moment it's spotted and properly identified. These teams had set out expecting to measure exactly how much the universe's expansion was slowing down over time, since gravity, pulling all of the universe's matter inward on itself, should have been gradually decelerating that expansion ever since the Big Bang. The same basic expectation that had led Einstein himself decades earlier. To assume the universe should be static rather than expanding at all before Hubble's observations proved that assumption wrong. Instead, both teams found the opposite. The universe's expansion wasn't slowing down at all. It was speeding up, accelerating, with distant galaxies receding from us faster than they should be if gravity alone were governing the universe's large-scale behavior. Both research groups, working independently of each other and initially quite skeptical of their own surprising results. Given how thoroughly it contradicted the prevailing expectation at the time, spent considerable additional effort double and triple checking their measurements, looking for any possible systematic error that might explain away such an unexpected finding, before eventually becoming confident enough in the result to publish it. Researchers on both teams have since described that period of double-checking as genuinely stressful, going back over every step of their analysis, questioning every assumption, half expecting to eventually find the mistake that would make the surprising result quietly disappear. The way careful scientists are trained to treat any result that seems to overturn decades of prior expectation. When the mistake never turned up, and when both independent teams, using different telescopes, different supernovae, and slightly different analysis techniques, kept arriving at essentially the same accelerating expansion conclusion, the result finally became something the broader scientific community had to take seriously, however uncomfortable it initially felt. This discovery was significant enough that the leaders of both research teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, shared the Nobel Prize in Physics in 2011 for the finding. A genuinely rare case in modern astronomy where two independent, competing research teams essentially reached the same startling conclusion at almost exactly the same time, each serving as an independent confirmation of the other's otherwise almost unbelievable result. Whatever is causing this accelerating expansion, and physicists still don't have a complete, settled explanation for what dark energy actually is at the deepest level. It has to be present everywhere, in the empty space between galaxies just as much as anywhere else, actively working to push space itself apart, everywhere, all the time. A kind of built-in expansive pressure baked into the very fabric of space itself. In the space between two distant galaxies, dark energy isn't just present as an inert background ingredient. It's actively doing something, contributing a small but genuinely real outward push that, summed up across the enormous distances separating galaxies, is gradually winning out over gravity's pull, slowly accelerating the rate at which those galaxies drift apart from each other, a process that will, according to current models, continue and even intensify across the almost unimaginably long future stretching ahead of the universe. There's one more genuinely surprising ingredient worth adding to tonight's picture before we bring everything together, and it's the one component on this entire list that isn't invisible, isn't diffuse gas, and isn't some exotic form of matter or energy at all. It's stars. Actual, ordinary stars, sitting alone in intergalactic space, gravitationally unbound to any galaxy at all, quietly drifting through the vast gaps between them. The idea that individual stars might exist completely outside of galaxies was first proposed as early as 1937 by the astronomer Fritz Zwicky, studying the Coma Galaxy cluster and noticing that the cluster's overall brightness pattern hinted at a population of stars scattered outside of any individual galaxy's boundaries. Zwicky, incidentally, is the same astronomer whose earlier work studying the Coma cluster's overall mass, using yet another independent method involving how fast individual galaxies moved within the cluster, provided some of the very first hints of dark matter's existence. Decades before Vera Rubin's more famous rotation curve measurements brought the idea into mainstream acceptance, making Zwicky a genuinely remarkable, if underappreciated, figure connecting several of tonight's separate threads together, decades ahead of when the broader scientific community was ready to take his more speculative proposals seriously. Zwicky measured how fast individual galaxies within the Coma cluster were moving relative to each other, and found they were moving so quickly that the cluster's visible mass, based on all the stars and gas astronomers could actually see, simply wasn't enough gravity to hold such fast-moving galaxies together at all. Meaning, the entire cluster should have flown apart long ago if visible matter were truly all there was. He proposed in 1933 that some additional unseen mass, which he called Dunkel Materie, dark matter in his native German, had to be present to provide the extra gravitational glue holding the cluster together. An idea that sat largely ignored for nearly 4 decades before Rubin's independent. And far more widely accepted, rotation curve work finally brought the concept back into serious scientific consideration. It took another 60 years for astronomers to actually confirm this directly. In 1997, using the Hubble Space Telescope, astronomers identified the first genuinely confirmed intergalactic stars in the Virgo galaxy cluster. Individual stars sitting isolated, sometimes hundreds of thousands of light-years from the nearest galaxy with no gravitational connection to any single galaxy at all, orbiting instead within the broader gravitational potential of the entire cluster. Confirming this required an extraordinarily sensitive instrument capable of picking out the faint light of individual, isolated stars against the vast, largely empty backdrop of intergalactic space within the cluster. A technical achievement that simply wasn't possible with earlier generations of ground-based telescopes, hampered by the blurring effects of Earth's own atmosphere. Limitation space-based telescopes were specifically designed to overcome. These stars are generally thought to arrive in intergalactic space through one of 2 main mechanisms, and both have been observed happening in real, ongoing galaxy interactions. The first is tidal stripping, where the gravitational forces involved in a close pass or collision between galaxies literally pull stars loose from their original galaxy, flinging them out into the surrounding space. A process visible in real time in systems like the colliding galaxies nicknamed the Mice, located roughly 300 million light-years away where long. Stretched out tails of stars and gas trail behind each galaxy as they tear at each other gravitationally, streaming out into space in exactly the kind of elongated tidal tail that eventually deposits some fraction of its stars permanently into intergalactic space, rather than pulling them back into either galaxy once the interaction settles down. Picture 2 galaxies passing close by each other, each one's gravity reaching out and grabbing hold of the stars nearest to the other galaxy, stretching them out into long, curving streams that can extend for hundreds of thousands of light-years beyond either galaxy's original visible disk. These tidal tails are actually visible directly in photographs of ongoing galaxy interactions. Glowing arcs and streamers of stars and gas stretched out like taffy pulled between 2 hands, tracing the exact gravitational choreography of the encounter. sometimes remaining visible for hundreds of millions of years after the initial close pass, slowly dispersing and fading as the stars within them gradually spread out and lose their coherent, streamlined shape. Some of the stars caught up in these tidal tails eventually fall back into one galaxy or the other, pulled home by the gravity that originally held them. But a meaningful fraction end up with just enough velocity, imparted by the violence of the interaction itself, to escape both galaxies entirely, left drifting freely within whatever broader cluster or group those two galaxies happen to belong to. A permanent one-way departure from the galaxy that originally hosted them, with no possibility of ever finding their way back home again. The second mechanism involves individual stars getting flung out at extraordinary speed after a close encounter with a supermassive black hole, the kind that sits at the center of most large galaxies, gaining enough velocity from that close gravitational encounter to escape their home galaxy entirely, becoming what astronomers call hypervelocity stars. This mechanism relies on a genuinely fascinating piece of orbital mechanics. If a pair of stars orbiting closely around each other happens to wander too close to a supermassive black hole, the black hole's gravity can capture one star into a tight orbit while violently flinging the other outward at extraordinary speed, sometimes exceeding 1,000,000 miles per hour. More than enough velocity to escape the entire galaxy's gravitational pull and head out into intergalactic space permanently. Astronomers have actually identified specific hypervelocity stars in our own galaxy's outer halo, showing exactly this kind of extreme unbound velocity, their trajectories tracing back toward the general direction of the supermassive black hole sitting at the Milky Way's own center. A genuinely direct piece of evidence for exactly this ejection mechanism happening in our own cosmic backyard. The first such hypervelocity star was identified in 2005, moving fast enough relative to the rest of the galaxy that it's genuinely on track to escape the Milky Way's gravitational pull entirely. Given enough time, one of only a small handful of stars anywhere known to be moving with that kind of extreme, unbound velocity. Since that initial discovery, astronomers have identified a modest but growing catalogue of similar hypervelocity stars, each one adding to the broader picture of exactly how individual stars, over the vast span of cosmic time, gradually get ejected from their home galaxies and begin the long, solitary drift into intergalactic space that eventually, for at least some small fraction of them, ends with them becoming exactly the kind of isolated, rogue star population we've spent this section of tonight's video discussing. The scale of this rogue stellar population turns out to be genuinely surprising. Astronomers now estimate that these unbound intergalactic stars can account for somewhere between roughly 10 and 50% of the total stellar light within a massive galaxy cluster, an enormous diffuse glow called intracluster light, faint enough that it went undetected for decades, but substantial enough, once properly measured, to represent a huge reservoir of stars existing completely independent of any individual galaxy. This intracluster light presented its own detection challenge, not unlike the one astronomers faced with the warm, hot intergalactic medium, just for entirely different physical reasons. It's not that these stars are too hot or too diffuse to see, the way the WIM was. Individual stars genuinely do emit plenty of visible light. The problem is that this light is spread out over such an enormous area, and each individual patch of sky contributes such an extraordinarily faint, low-surface brightness glow that it took specialized deep imaging techniques, carefully designed to detect extremely subtle, extended sources of light rather than the sharp, bright points a normal photograph is optimized to capture before astronomers could properly measure and map this diffuse population at all. Standard astronomical imaging, optimized to pick out sharp, bright, discrete objects like individual stars or the compact, glowing cores of galaxies, tends to actively work against detecting something like intracluster light, which is spread thin, faint, and diffuse across an enormous area rather than concentrated into any single bright, easily distinguished source. Researchers had to develop entirely new processing techniques, combining extremely long exposure times with careful patient image stacking and background subtraction, essentially teaching their instruments to notice an incredibly faint, extended glow that conventional imaging methods had been quietly discarding as background noise for decades, simply because nobody had yet built the specific tools needed to properly separate that faint signal from everything else cluttering the frame. In the Virgo cluster specifically, astronomers estimate there could be as many as 1 trillion individual rogue stars, drifting freely within the cluster's overall gravitational field rather than belonging to any one of its roughly 2,500 member galaxies, a population so large it plausibly rivals, or even exceeds, the combined stellar population of many of the cluster's smaller member galaxies put together. 1 trillion individual stars, none of them belonging to a single galaxy, orbiting instead the combined gravitational pull of an entire cluster, is a genuinely staggering number to sit with, larger than the total star count of many individual galaxies. All of it hiding in plain sight as a faint, diffuse glow that took astronomers decades to properly characterize and measure. Closer to home, astronomers identified a population of more than 600 rogue stars in 2012, sitting at the outer edge of our own Milky Way, in the general direction of the Andromeda Galaxy, evidence that our own cosmic neighborhood has already begun contributing its own scattered stars to this vast, diffuse population. It's a genuinely strange thing to consider. Somewhere out past the edge of our own galaxy, in the general direction of our nearest large galactic neighbor, hundreds of individual stars are drifting alone, no longer gravitationally tied to the Milky Way. Their own small individual contribution to the exact same kind of scattered stellar population astronomers have measured in much greater abundance within larger, richer galaxy clusters like Virgo. So let's finally bring everything we've covered across tonight's entire story together and give the honest, complete answer to the question we opened with. What actually exists in the space between galaxies? It's not nothing, and it's also not remotely what most people instinctively picture. It's an almost unbelievably thin scattering of hydrogen and helium gas, the literal leftover material from the universe's birth, heated in many places into a scorching, diffuse plasma called the warm, hot intergalactic medium, holding within it nearly half of the universe's entire supply of ordinary matter, arranged along an enormous cosmic web of filaments stretching hundreds of millions of light years, surrounding vast, genuinely near empty voids. Underneath and around all of that ordinary matter sits an invisible scaffold of dark matter, outweighing the ordinary matter by more than 5 to 1, the actual gravitational architecture the entire cosmic web is built on, detected across nearly a century of independent converging evidence. From Vera Rubin's rotation curves to the bullet cluster's dramatic separation of matter types without ever once being directly captured or observed. Permeating everything, uniformly, everywhere, sits dark energy, quietly pushing space itself apart, accelerating the very drift between galaxies that first inspired tonight's question. confirmed through the genuinely surprising discovery in 1998 that the universe's expansion is speeding up rather than slowing down. And scattered throughout it all, rarer and stranger than any of the rest, drift individual stars, torn loose from their home galaxies through tidal stripping or violent encounters with supermassive black holes, orbiting nothing but the broad gravitational pull of entire galaxy clusters. Silent, isolated points of light with no galaxy left to call home. That's a genuinely remarkable answer to arrive at, especially compared to where we started tonight, with a simple, almost throwaway assumption that the space between galaxies was close to perfectly, boringly empty. It turns out that gap, that vast stretch of apparent nothing separating one island of stars from the next, contains a working model of almost the entire universe's actual composition. In miniature, ordinary matter, dark energy, and even the occasional rogue star, all present, all measurable, all quietly filling in what most of us, myself included, before I started genuinely researching this specific question, had simply assumed was empty space. Think about what that actually means for the next time you look at a photograph of two distant galaxies, separated by some vast, dark gap of apparently empty space. That gap isn't a blank backdrop, a placeholder region of nothing separating the two objects the photographer actually cared about capturing. It's a genuine physical environment in its own right, containing its own specific mixture of ancient gas, invisible scaffolding, and accelerating expansive pressure, and somewhere within it, quite possibly an isolated star or two, drifting alone, belonging to nothing, and yet still undeniably, genuinely there. There's a specific kind of satisfaction available in finally having the complete, honest version of an answer like this one, rather than the comfortable, oversimplified version most of us walk around carrying by default. It would have been easy enough to end tonight's story after the first half, with the intergalactic medium and the missing baryon problem, and call it a complete answer. It wouldn't have been dishonest, exactly, just incomplete, leaving out the two ingredients, dark matter and dark energy, that actually make up the overwhelming majority of everything genuinely present in that vast, dark gap between galaxies. Getting the complete picture required following the evidence past the point where a simpler, tidier story might have comfortably stopped. And I think that's exactly the kind of thoroughness a question this genuinely interesting deserves. So here's what I'd like to know, now that we've walked through the complete answer together. Earlier tonight, I asked you to guess what's actually out there in the space between galaxies. Now that you've heard the full picture, tell me honestly in the comments which specific piece of tonight's answer surprised you the most. The fact that the emptiest cosmic voids are still less empty than a solitary particle per cubic meter, but genuinely aren't perfect nothing. The decades-long hunt for the universe's missing ordinary matter. The fact that dark matter actually outweighs everything you can see by more than 5 to 1. Or the strange, quiet population of trillion individual stars drifting alone through galaxy clusters with no galaxy to call home. I read every single comment, and I'm always curious which specific piece of a story like this one actually sticks with people once they've heard the whole thing laid out properly. I'll admit, when I first started researching tonight's topic, I expected the intergalactic medium and the missing baryon problem to be the most surprising part of the story, simply because it was the piece I personally knew the least about going in. It turned out, once I actually dug into the numbers, that the sheer scale of the rogue star population was the detail that genuinely caught me off guard. 1 trillion individual stars in a single cluster belonging to nothing isn't a fact I expected to encounter while researching a video that started with a fairly simple question about apparent emptiness. There's something almost poetic about a topic supposedly about empty space turning out to contain some of the most genuinely surprising, most emotionally resonant details in the entire conversation. Individual points of light with no home left to return to, quietly outnumbering entire galaxies worth of stars, hiding in a glow most photographs of the night sky were never sensitive enough to properly capture. If a topic like this can still surprise someone who spends considerable time researching it, I think that says something real about how much genuine strangeness is still hiding in plain sight. Scattered across parts of the universe most of us never think to look at closely. If tonight's video gave you a genuinely more complete, more accurate picture of what actually fills the vast majority of the universe's volume, subscribe. Because that's exactly the kind of question this channel exists to take seriously. The ones that sound simple on the surface and turn out to reach into some of the deepest, most actively researched questions in all of modern astronomy. Every single video here starts from that same basic premise. Take an assumption most people never think to question, and follow the actual evidence wherever it honestly leads. Even when that means overturning the tidy, comfortable picture you walked in with. Whether that assumption is about empty space, about the age of light, about the number of Earths quietly hiding out there in the cosmos, or about anything else worth genuinely questioning rather than simply accepting at face value. There's a genuine, quiet satisfaction in having walked all the way through this particular question tonight. From a simple assumption about darkness and distance to a complete, layered answer involving nearly every major component cosmologists currently believe the entire universe actually, genuinely, honestly contains, and I hope that thoroughness is exactly what you came here looking for tonight, genuinely. Rather than a shortened, oversimplified version that would have left half the actual story sitting quietly, unexamined, in exactly the kind of overlooked darkness this entire video has been about. A darkness that, as it turns out, was never quite as dark, or quite as empty as any of us had originally assumed once someone finally took the time to actually look closely enough and carefully enough to notice everything genuinely filling it in, patiently waiting there the entire time, long before anyone thought to build the instruments capable of finally proving it. Quietly, faithfully, exactly where it had always been, filling in the gaps between the stars. The whole time, whether or not anyone was ever watching closely enough to notice, waiting only for someone to finally ask, and finally, patiently, honestly, look. Until next time, the next time you look up at a genuinely dark, star-filled sky, spend a moment thinking not just about the stars themselves, but about the vast, quiet gaps between them, and everything actually filling those gaps that no telescope, no camera, and no photograph has ever managed to fully capture. It's not empty. It never really was. It's simply been waiting patiently for us to build the right instruments, ask the right questions, and finally notice everything that was there all along, quietly filling in the darkness the entire time. Long before anyone thought to look closely enough to see it, an ancient, invisible, accelerating, occasionally starlit fullness, hiding in plain sight inside every single dark, empty-looking gap the night sky has ever shown you. A quiet, honest fullness, hiding in the dark, waiting to finally be seen.